let's see, why is my, I guess that's right. Okay, so let's see, I think y'all start with this one. Is that true? So the first one on your page. Yeah, ball is thrown horizontally from the top of a 60-meter building and lands 100 meters from the base of the building. Ignore air resistance. The first question you need to ask in this problem is, how long is it in the air? So what tack are you going to take to find the time that it's in the air? What information? Huh? Right, so we know the y motion, it does what? Basically just drops, right? From what distance? Right, yeah, so it drops 60 meters, and so we can use that to find our time. I'm going to go ahead and write our equations up here up top while you're working on finding the time. I basically have a set of 3 equations. So my first thing is to find the time. I'm going to use my y motion. So from the information that's given, I can determine how far it falls. I'm going to go ahead and start writing down everything that we know over here as well while you're working on the time. So we know it drops 60 meters. How long does it take to drop 60 meters? That's the first question. 3.5 is right. That's right. So I just say that y equals v naught yt plus 1/2 ayt squared. This is made easier because v naught y is equal to 0 because all of my velocity, it says, is horizontal. And so I have negative 60 equals 1/2 of negative 10 times t squared. And I solved that for t, and as Jay said, it's 3.5 seconds. So that's my total time in the air. Usually you're going to use your y motion, your y displacement, in order to, or your y motion to find the time in the air. So we've done several problems like this. You have that problem where it goes up and then comes back down again. You can, take the velocity at the top of 0 and determine the time in that way. In this case, we know the displacement in the y direction, so it's just like something dropping from 60 meters in the air, and so we can find our displacement here, our time in the air there. And then in this problem, if we were given some slightly different information, so say instead we weren't given y here, we weren't given the 60 meters, but we were given an initial velocity, then you could find the time there, because if you know the initial velocity and you know the x displacement, then you can find the time by this x equals vxt up here. Alright? But in this case, you wanted to use your y displacement. A couple things to note is, or one thing to note here is that I use negative 60. That's because I set y naught equal to 0 here. That's my initial position, and it was dropping 60 meters. If you didn't set it to negative 60, you'd wind up with a square root of a negative number, which is imaginary. So that would be a problem. All right, so let's do part B here. You might have already done it. In part B, we just want to know the initial horizontal component of the velocity. So that is, what is Vx equal to? We know that in 3.5 seconds it travels 100 meters. So what is Vx? Should be pretty quick. Find the x component of the velocity. Watch, Michael? That's all. I mean, that's a calculator on your watch? Cool. It's a smart watch. Okay. We had calculator watches when I was in grade school, but they had the little buttons on them, but they were actual calculators.
So I should have seen those.
Oh, yeah. They still have them? All right, what is Vx then?
17.9.
No, he travels not 60 meters, he travels 100 meters in the expression, right?
28.6.
What did you get?
28.
Yeah, so 29 meters per second. So I say x is equal to Vx times t, right? I know x and t, so I just say Vx is equal to 100 meters. Divide my time, it's 3.5 seconds. Let's call it 29 meters per second. What is Vy? V naught y? What's the initial velocity in the y component, in the y direction? And it is what?
0.
It's 0, right. So it's not moving in the y direction at all. It's just moving horizontally. Part C asks what is the vertical component of the ball just before it hits the ground. So part C, I want to know right here, what is Vy? Go ahead and try that out. By the way, you had a homework question that was very similar to this, but just to give you a little extra practice. You got it, Courtney? You got it? Daniel? Okay, negative 35 is right. I'm traveling here for 3.5 seconds, and this object drops at a rate by the acceleration due to gravity, and it drops at a rate of 10 meters per second per second. So every second, it increases in speed by 10 meters per second. And since it goes for 3.5 seconds, it goes 10, 20, 30, 35 meters per second. All right, it's accelerating at negative 10 meters per second squared at this rate. It starts out at t equals 0 and goes for 3.5 seconds. So then it goes up to 35 meters per second. We could just, if you want to use the formula, you can think about it in this way. So Vy is equal to V naught y plus Ayt. V naught y is 0, and so that's just going to be negative 10 meters per second, meters per second squared, times 3.5 seconds. And that's equal to 35, or negative 35 meters per second. The negative coming about here because it's in the downward direction. And then for the very last part of this question, it just wants to know what is the magnitude of the speed. So if we look here, we have two components. My Vx, which we've already said is 29 meters per second, and my Vy, which is negative 35. So what is the magnitude of the vector made up of those two components? I have an x component of 29, a y component of 35. What is the magnitude of that vector? And again, you'll have just a basic vector problem, adding or subtracting vectors, like we did in class in the pre-response part. But it could also be another problem as well.
I think I have it.
What do you think you have?
45.
45 is right, yeah. So I have these two vectors. I want to draw them a little bit differently. 29 in this direction, 35 here. I want to know the length of this vector. So as Josh did, I just say square root of 29 squared plus 35 squared. I just left the negative off. It goes away anyway because it's squared. And that's equal to 45 meters per second. If I wanted, I could also find this angle, do the inverse tan of 35 over 29. If you're not familiar on how to do that, you need to do it, because there will be a question. I'll just give you a series of vectors, and I'll ask you to add or subtract those vectors. I'll say, give you vectors A, B, and C. What is A plus B minus C? What is A minus C plus B, or something like that. So make sure that you can find the magnitude and direction of a resultant vector. All right, let's try this next one. Hopefully that was pretty easy for you. We've done examples like this, and there are homework questions for you. But if it's not easy, that's okay, because our test isn't for another week. If it's not easy, just make sure you look at the homework. I suspect if it's not easy, you haven't done the homework yet. The homework will help you with this. And also look back at the old tests. There are some very similar questions to this in the homework. Let's see. Let's look at this one. Let's see. Yeah, let's go and do this one. I have this volcano. It ejects red hot rocks and lava, and a rock is ejected at 25 meters per second at an angle of 23.57 degrees above the horizontal. And then it strikes the side of the volcano at an altitude that's 5 meters lower than its starting point. I want you to calculate the time and then the magnitude and direction of the rock's velocity at impact. So what we have here is a rock that's ejected. And it follows a path like this. And I know that its final position is 5 meters below where it started. And I want to know the time. You will need the Pythagorean theorem for this. And I know I told you all this, or not Pythagorean theorem, what's it called? The quadratic equation. I did tell y'all before that you wouldn't have to use the quadratic, but you might see it on this next test. I'll provide the quadratic for you. I don't know, some of your calculators will actually solve a quadratic equation, I'm aware of that, but I want to see it worked out with the quadratic equation. But I will provide that equation. It looks like this. If I have an equation that's of the form at squared plus bt plus c equals to 0, then I can say that t is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. That'll give you two answers. A quadratic equation always has two answers because it's squared term. And you just take the positive answer for time. How would you go about finding the time when it's at that position? Tom?
Separate the time into two parts. One part is a parallel, and second part is 5 minutes of free fall. So you add two of them together and get the whole time.
Okay. Yeah, you could do that. That would be okay. Here we're saying you could determine the time that it takes to get from here to here, like in that Gone in 60 Seconds clip, that's that same problem, right? We say the velocity up here is 0, and then you can find the time at this point. And then you say, well, you have to find the initial velocity here, right, in the y direction, and then solve for how much more time does it take to go this distance. You could do that, yeah. There's a slightly easier way. Does anybody know? I'll explain to you it. It reminds you of those equations. Well, maybe not easier, but fewer steps. You have x equals vxt, and then y equals v naught y t plus 1/2 ayt squared, and then vy equals v naught y plus ayt. Any of these equations you just have one unknown for? Which one? The V one? This one right here? Let's see, Vy, well, it's sort of going back to what Tom said. Yeah, we do know this at the top, right? Because we know Vy is equal to 0. We also know V naught y and Ay, and then we can find T top, which we've done before, right? To find the total time of the trajectory. What about this one? What are the unknowns in this equation? Okay, well, we know y, though. At the very end, we know that y is equal to -5. So given that we know that it lands -5 meters below where it started, we can solve this equation then for t, and we'll find the total time in the year. Let me show you. So we haven't done this because we tried to shy away from using the quadratic, but it can make a problem just like a single step problem to use the quadratic. So let's see. So I would have y is equal to -5 meters. I say -5 because here y naught is equal to 0. V naught y. Somebody tell me what V naught y is?
Would it be the y component of the vector they gave you, the 25 meters per second?
That's right, yeah. So V naught y is the y component of our velocity, and we find that by our velocity times what? That's right, sine of the angle. So this is going to be 25 sine of 23.57. Times t, and then 1/2 of a is -5 t squared. Right, so go ahead and try solving that with the quadratic equation. I set it up so the numbers are really simple, so it should fall out pretty easily. First, you want to put it in this form. It's at squared plus bt plus c equals 0. So you're going to basically take everything over to this side. You have 5t squared plus whatever this, minus whatever that is, times t. -5 equals 0. Is it true that your TIs can solve a quadratic putting in those terms? Do y'all know how to do that?
I believe it has to have the CAS version.
Oh, really? The CAS version?
Which is the algebraic system.
Oh, I see. Okay.
It will solve with variables.
Yeah. All right. If your calculator can do that, it's a useful thing to know how to utilize. So. Does anybody have this 25 sine 23.57? Okay, so we'll just call it -10. So minus 10t minus 5 equals 0. So that's the equation you're solving for the quadratic. You have it there? What is it? One second. No. No, that's not right. Yeah, so 2.4. 2.4 is right. I'm going to start filling in the numbers up here, okay? Y'all keep going. If you haven't used the quadratic very often, it can be a little cumbersome to use.
So in this class, every time we try to solve a quadratic, we should just use the equation, or can we like try to factor it if it looks simple enough?
Oh, you couldn't factor this, could you? Or can you factor it, actually?
I tried and it didn't work out, but...
Yeah, I mean, you're not going to get a simple factor. Yeah, the numbers. I'm not going to try to produce an equation that's factorable. So yeah, I would just use the quadratic equation. Alright. So this is 10 plus or minus the square root of 100, or excuse me, 200 over 10. And so that's 10 plus or minus 14 over 10, 24 over 10, which is 2.4 seconds. Notice you also get another solution to this. It's like negative 0.4 seconds. But that's not a real solution to this because you can't have a negative time. Alright. And then if we want to know the magnitude and direction of the rock's velocity at impact, remember these are just functions, so I can determine the velocity in the x direction and the velocity in the y direction. Well, I know the velocity in the x direction is just the x component of the velocity, and then I can determine the velocity in the y direction at that time at 2.4 seconds just by plugging into that. So those are just functions, and so we need to know the x and the y components of the velocity at this point. Y'all can tell me what those are when you get them. case? Sorry.
How is to solve the y position function?
I'm sorry, what now?
If I was to solve the y equals v naught y t,
Uh-huh.
if I was to solve that for t, then plug what I got into the y function for t, would that give the same, like, I think velocity?
It would give you the velocity at this point. So yeah, you want to use it. Is that what you're asking?
Yeah.
Yeah, that would give you the velocity at this point. Right, these are just functions. Anytime that I plug into them will give me the velocity at that point. So if I know the time when y equals -5 meters, then I can also find the velocity by taking that time, 2.4 seconds, and plugging it in here. And then solving that for the velocity in the y direction.
You know what I'm saying? Like, if I didn't find the time, but if I just solve for t and then plug that into the other function, like solve.
Oh, you substitute it in? Right. Yeah, you can do that. I mean, we're going to do that in the next problem, solving it by substitution. But sure, you can do that. They're probably saying that you could solve it by substitution. You could solve this thing for t, right? And then plug that in up here to get dy in terms of y. Is that what you're asking? Yeah, you get a velocity function in terms of the y position. Okay. That could be useful, but it's going to be complicated. The algebra will be complicated. So you're solving that quadratic for t and then plugging it back in. That would be a little complicated. All right. Does anybody have dx for me? Dx here? 23. I think that's right. Let me check. Yeah, that's what I got. So it's 23 meters per second. Does anybody have y for me? Vy? That's the initial y. Yeah, so this v naught y is 10 meters per second. Minus 10 times 2.4. So my vy is what? Negative 14. Right, negative 14 meters per second. So I have Vx is 23 and Vy is negative 14. If I want to know the magnitude of the resultant vector,
So initial y velocity isn't negative?
the what now?
The initial y velocity?
No, the initial y velocity is up and in this direction. Right? It's 10 meters per second up. And then it goes up. Right? It stops at the top, and then it comes back down. Here it has negative 10 meters per second, and then in the time required to get from here down to here, it gains an additional 4 meters per second. All right, so it probably took about half a second. All right. So then I can find my resultant. At that time, square root of 23 squared plus 14 squared. Just drop the negative because it's squared, and I get 27 meters per second. And I can find the angle too. I'll leave you to do this on your own, but it's the inverse tan of the y over the x component. It's 14 over 23. That's equal to 31 degrees below the plus x-axis. Make sure that you give the details about that angle, how it's measured. Okay. Like if you just put 31 degrees, I can count off, I don't know, a couple points probably. All right, let's do one more. This one requires that you substitute one equation into another. I would be prepared for that on the exam, that you have to solve a system of equations by substitution. Not a terribly complicated system, but a system of two equations. Because you come to a point where you have two equations with two unknowns each. And that's what we have here. So we have a soccer player, kicks the ball a distance of 30 meters towards the goal. I want to find the initial speed if it just passes over the goal 2.4 meters above the ground. I always like to draw a picture with this. So I have this soccer ball. It travels up. And then I know that over here the goal is 2.4 meters above the ground, and it just passes over it. I know that this angle is 40 degrees. I know that this distance is 30 meters. And that's all. That's all I know. Yeah, and then the acceleration, of course, I know in the x and y directions. Okay? And so I want to know the initial speed of the ball. How fast is the ball going? All right. I always like to write down my equations. So I'm going to write them here. I have x equals Vx, which is V naught cosine theta. Times t. Alright, what are my unknowns? Here I've written these slightly differently. I've gone ahead and expanded these Vx and Vy terms, so this is usually we write Vx, and usually here we write Vy. Well, what are my unknowns in these equations? What are some things that I don't know? And what are some things that I do know? How about the first one? What do I know and not know? Right here, at particular points.
You don't know initial velocity.
Okay, I don't know V naught. In fact, that's what it's asking for. V naught. Do I know theta? Yeah, do I know t? No, I don't know t. But I do know the x at a particular time, right? I know the x over here at 30 meters. Oh, there's something else I haven't drawn on this. What is that?
The
Height of the goal.
Right, the height of the goal. Right, so let me write that here. That'll be pretty important. So I know this distance is 2.4 meters. Okay, so I have two unknowns in this first one. I don't know V naught, and I don't know t. And then in the second one, what are my unknowns? The second equation right here. At a particular time, or a particular position.
time and initial velocity.
Right, so again, I have time and initial velocity. Alright, so I don't know the time, and I don't know the initial velocity. Alright, so here I have a system of two equations. At a particular point, they're going to be described in the same situation. So at this point, I both know the x and the y. Right? So I know that at this point, these two equations will describe the same time. You follow what I'm saying? And I know the x and the y at that point, which is the same time. They're coincident. And so I can solve them given that information. So this is I'm going to take these two equations and solve one for something, and then plug that back into the other. All right, what do I want to solve here? Which equation will I solve to substitute into another equation?
Wouldn't it be easier to solve for t in the first equation than plug it into that?
Right, yeah, so we're looking for V naught. So it would be easier to solve for t in the first equation and plug that into the second. So I can say here that t equals x over V naught cosine theta. And then I'm going to take this, I'm going to plug it in here, I'm going to plug it in here. Let's go ahead and just write out that y equation, but now substituting t with x over V naught cosine theta. The algebra here gets a little bit cumbersome, but if you're careful when you're writing things out, you can track it along fairly simply. Guys, if you have trouble solving systems of equations, now's a good time to master it, because we're going to be doing it all year. Later, we'll look at some different ways to solve systems of equations, which can be very useful for computing. All right, I'm going to start filling this in. I have so that's what I have. And now I want to get V naught here. I can make some simplifications here. My V naught here cancels out, which makes it a lot easier to solve for V naught by losing that term. I think that's it. Yeah, I can also simplify it a little bit more. Sine over cosine is what? Tangent, right? So it's not, you don't have to do it, but it makes it a little bit easier. So if I get rid of the sine and cosine, and I can write in a tan theta. All right, so I have y equal tan theta x plus that whole thing. Now I want to just isolate my v naught. So I'm going to do subtract tan theta x from both sides. So I have y minus tan theta x equals 1/2 and all the rest is just algebra. Then I'm going to multiply both sides by 2, divide both sides by ay. That gets rid of that and that. Let's see. I'm going to invert both sides. You might do this in slightly different order. But if I invert both sides, that is, raise both sides to the -1 power, I get ay over 2y minus 2x tan theta is equal to v naught squared cosine squared theta over x squared. I just took the inverse of both sides. And now let's see, what do I need to do? I'm going to divide both sides by cosine squared theta. That gets rid of that. And multiply both sides by x squared. That gets rid of that. And then I take the square root of both sides. And that'll give me v naught. Double check this is right. So, 0.4. Yeah, see, I even did it differently in my notes. So you might follow sort of the order differently in your algebra. But if you put in the numbers here, you find that the velocity is 11 meters per second. All right. In your homework, there are some others where you solve systems of equations. Just make sure that you're up on that you're able to do so. It comes up again in chapter 4, solving a system of 2 equations. What's up, Tom?
Mathematics is 18.4.
I don't think that's right.
Because we exact same equation.
Did you do it differently?
No, exact same equation. Except the g is minus.
Oh, okay, yeah. So there it is. Alright. Alright guys, y'all can solve a system of equations on the test. You should have had it, but a lot of students don't really have sort of lost that skill. So make sure that you can do it. It's very important. Alright? Alright. And be happy about it. Solving systems of equations, because it's very important when you're dealing with physical systems. You often have multiple equations describing those systems with multiple unknowns, and it's important to be able to get to the actual knowns. All right, let's see. Let's move on now to chapter 4. You'll feel like projectile motion is dead and gone? Like, feel like you could do this? If you were just with a blank sheet of paper in front of you? Alright, it'll help you to work through the homework. There's a lot of practice in the homework, and that'll be similar to questions that you'll have. So, again, likely to see solving a system of equations. Could see the quadratic equation. I'll give it to you if you need it. And from chapter 3, you'll also see vectors. Primarily in the free response, it'll be adding vectors numerically, but you could also see, I could ask you also to just sketch them out properly, the way, like in the proper quadrants in all our business. All right, let's move on to chapter 4 then. Chapter 4 deals with Newton's laws. The laws of motion. A force, sort of like the first grade definition of force when you study it in first grade. You'll study forces in first grade. and sort of like basic laws of motion? Probably did. First, second, third grade, they start to introduce it. A force is just a push or pull on some object. So it can be any number of things. It could be like a fight. Y'all ever get into a fist fight when you were kids? How many of you got into a fist fight? You did, Chase? Yeah, me too. Nelson Zamora. He and I got into a fist fight. Nobody really won, I think. And even at the end, we just sort of, I don't know, we thought we were supposed to fight, and so we went and we fought, and then at the end we like shook hands, and then we were fine. So, but we both sort of walked away with bruises all over us. So I don't think anybody won. I think we both lost. But anyway, that's a type of force, right? Whenever you hit somebody, because it's a push or a pull on something. You can have ropes or tension in ropes or strings or cables or whatever. That's the force. You can also have frictional forces, which we'll deal with in this chapter. We can also have forces that don't require contact between things. So all those forces that I mentioned are what we call contact forces. But then you can also have forces that don't require contact, and those are called field forces. What's an example of a field force?
Centripetal force?
No. A centripetal force, we'll talk about that in chapter 6 or 7. It actually does, you can have contact or not. Okay, a magnetic or an electric force, electromagnetic forces don't require contact. But one other one that we've dealt with a lot already is what, Shane? What's the force that we've dealt with that doesn't require contact? Gravity. So the gravitational force and the electromagnetic forces are the big field forces. So we have two types of forces. We have contact forces and field forces. Contact forces require contact, so hitting something, friction, tension, all these are contact forces. And field forces include or don't require contact. We'll talk about these a little bit more. And actually, at the end of towards the end of the semester, we'll deal with field forces more. So we'll deal with the gravitational fields, and then next semester we'll get into electric fields. Fields are really just a way of describing forces. So a field, we use that to represent the force that an object feels. So when you get close to a charged particle, it puts out like this electric field, which is really just sort of a man-made construct that we use to describe the force that an electric particle feels, or charged particle feels near another charged particle. When we're talking about field forces, there are four types. There is the gravitational force, this occurs between objects of mass. Objects so it's not just between you and the planet Earth, it's also between you and any other object of mass. So there is a gravitational force between each of you right now. You can calculate it, it's small, but it's actually measurable to have the gravitational force between sort of earthly bodies is a measurable force. You can do that in the lab. There are some very sensitive balances that you can use to measure those forces. There's also the electric force, which we'll deal with next semester. It's part of the magnetic force, but we'll just sort of clump them all together. This is between objects of charge. Particularly important for you chemists. And you'll get into that a lot in PChem. And then there's a couple others. We're not going to talk about them here, but you sort of need to know that they exist. The strong and the weak nuclear forces. And the weak nuclear force. Just know that they exist. Know that there are four field forces. So these are different types of forces that don't require contact between the objects. These are atomic forces occur within the nucleus. All right. There has been sort of in the past couple of decades the sort of developing theory called, this is just an aside, but called modified Newtonian dynamics. Or to have a cool acronym, it's MOND, M-O-N-D, Modified Newtonian Dynamics. And in short, what they say here is that, and there's some fairly secure, I think, mathematics that backs it up, that, when we observe things on Earth, we observe how they move, and we call that Newtonian dynamics. So these are just things like that are normal size, normal mass that occur in real time. So an object falling, bodies interacting, and stuff like that. But modified Newtonian dynamics says that when these forces occur over very large distances, that they can change, that there can be extra perturbations or extra terms that come into describing the motion of those bodies that you wouldn't see otherwise. Very large scales, like on the scale of galaxies, or across the universe. And so what this says is that maybe Newtonian physics doesn't occur in the same way over very large distances. Occur as expected over very large distances. And that could affect like how we observe things that occur very far away from us. That's just an aside, just sort of know that exists. I go down from here, guys? All right. So Newton's first law. Y'all probably seen Newton's laws before, right? There's the first, second, and third law. I have a little video I want to show you first. These are Newton's laws that are sort of as we perceive them. This is a Veritasium video. I've shown you the Veritasium videos before, but this is him talking about Newton's laws of motion and how they're incorrect, or what he calls as incorrect laws of motion. But just to summarize them, right, there's the first law, which is the law of inertia, that says that a body is in motion, or excuse me, what does it say? What's that? Right, an object at rest remains at rest unless acted upon by a force. And then also that an object in motion will remain in motion unless acted upon by a force. The second is that F equals ma, force equals mass times acceleration. And then the third, what is that? That's the, for every action, there's an equal and opposite reaction. So for every force, there's an equal and opposite force. So let's just watch this video. I think it's about 4 minutes long, so it'll take us right up till the end.